Hello and welcome to a combined finalFluid and thinkingParticles tutorial video. We will do something different in this video. We will do more of an explainer video where we look at how we did the setup we just saw in the introduction of this video. Let's have a look at the scene. So in this scene we have a floor object, we have our domain, our finalFluid grid where we have our smoke simulation going on. And we have several other objects in this scene, including a helper object and our metal plate. We want to erode this metal plate, so that's our main goal. And for that, we need our acid to flow down. So we have a fluid simulation as well. Those fluid particles, our acid, is falling down onto the metal plate, bouncing off the metal plate and running down all the metal, and as it flows down it erodes away metal. So that's the idea, and while it is eroding the metal we want to create vapor particles. So these blue particles we see there, those are our vapor particles we create in the process. Let's have a look at the particle setup. At first we want to have a look at our particle groups. So the particle groups are made of acid, so these are all our fluid acid particles, and it has a subgroup. That's very important to remember. We have an inactive subgroup within the acid particle group. I will talk about it later why we did that. Then we have our metal plate, helper object, volume particles, and our acid vapor particle group, and this particle group will be used for our finalFluid simulation. The first thing we do is with an object to particle we bring in the metal plate. We store the metal plate in the metal plate particle group. So the metal plate is just a standard mesh, a box we have there in the scene, and we just pick that and store it in the metal plate particle group. Then we bring in the dummy helper and we store this in the helper particle group as well. So very simple, very straightforward setup in thinkingParticles. First bring in the objects you want to have in your simulations. Then the next thing is we create the particles with the flow emitter. We create all the particles in the acid particle group and not in the inactive group. So keep that in mind. All particles at first are created in the acid particle group. And then we have some settings where we control the amount of particles we want to create, and the position where we want to create the particles is derived from our helper object we just brought in with the object to particles. So the center of our dummy object is the position we use for our flow emitter. The next thing we want to have here is just a time interval. We want to have the fluid or the acid to flow between frame 0 and 40. So if I play back, we will see that at frame 40 the flow will stop. And that's exactly what we want to achieve with the time interval. And then we just assign a mass to the particles, and that's pretty all we need for our particle generation. The next step is our metal plate. We want to be able to erode our metal plate, so to chip away material from the volume of the metal plate. To do that, we need an OpenVDB volume grid or volume object. I create a assigned distance field. So we prepare that with a assigned distance field, and there's all kinds of volumetric grids we could generate. The next thing we do is we turn our metal plate, our box object, into a true volumetric object. And this is done with the shape to volume VDB, and it creates automatically assigned distance field. So if I were to activate now our OpenVDB setup down here, I just did that, and if we restart the simulation we can see now the mesh, the box object, is turned into a true volume, and with that we can chip away parts of this volume and recreate the surface all the time. So as we can see here right from the beginning, when the acid particles collide, parts of the metal plate are burnt away or chipped away or eroded away, however you want to call it. And the longer the acid is in contact with the metal, the more it eats away of the metal. until it burns a hole through the metal plate. So this is a pretty simple setup, but it's amazing looking, and we can deform or erode away parts of our metal plate. And I'll explain later how we do that. But for now, let's just have a look at the simulation setup, the whole simulation of our acid. So the first thing we want to make sure is our acid particles, including the subgroups. We want all acid particles to be affected by gravity. And we set a gravity value, and that's it. Very easy setup. All particles have gravity now, so they flow down the metal plate. The next thing is our fluid simulation. We use for our fluid simulation our standard SPH fluid solver, which is very powerful in thinkingParticles, easy to set up, very predictable, and really fast. And we want to make sure that our fluid is affecting all the particles, including subgroup. So all acid particles, inactive or not, should behave like a fluid. Then we have our other fluid setups, and the next important thing is our boundaries, our collision objects. So we want to collide with a metal plate, so we make sure the metal plate is a collider, and we also want a collider object, a special collider object on the floor. And we use our SPH solver to simulate the fluid flowing down and splashing around. So very straightforward, easy setup for the fluid part. Now let's have a look at the acid part. And you might be surprised why there are so many nodes to simulate the acid, and I'll explain in detail what the idea and thoughts is about that. The first thing I want to make sure is that our final fluid smoke simulation or vapor simulation is not overloaded or gets too much data. Because we are using special particles to drive the smoke effect, I want to make sure that our vapor particles are really controlled when we create this effect. So these vapor particles should be created whenever there's a collision with the metal plate. And if we have this collision happening, we create these vapor particles. So all the vapor particles are created with the position borne, we can see here. So one particle for each acid particle. However, as I mentioned before, I don't want to have too many vapor particles for our final fluid simulation. So what we are going to do is restrict the amount of vapor particles we are going to generate. Because when we go into our fluid grid, we see we have a fluid emitter going on, and this fluid emitter creates our smoke, and the emitter is the actual particle, and it's the particles of thinkingParticle, we picked it here, and the acid vapor group. So I want to make sure I don't pump too many particles in there, because there might be just way more vapor, so it turns into a burning fire, hellfire. We don't want that. We just want this thin vapor to happen. So we need to make sure we are not creating too many particle emitters for our final fluid simulation. So how do I do that? The first thing we need to take care of is that when we have the particles flowing down, we only create these vapor particles when we collide or have a collision happening with the metal plate. I don't want to have vapor particles in air or when it's outside of the metal plate. So how do we achieve that? The first step is to reduce the amount of particles is I use a random generator. So the random generator creates for each particle a random number between 0.1 and 1.1. So whenever this is 1 or bigger than 1, greater than 1, I want to create a vapor particle. So whenever our random value is greater or equal to 1, we create a vapor particle. The next condition is I only want to create it when there's a collision happening. So I use the flow data and get the is collided output. And whenever there's a collision, I want a vapor particle to create. So this is my next input for the AND operator. So when we have a random number 1 and a collision happening, only then I will create my vapor particle with a position born. However, I have a third condition. I only want to do that on my metal plate and not on the floor, which also creates a collision. So I'll have this threshold on the C value, and as long as the C value is within these ranges, I will create vapor particles. If it falls outside of this range, I'm not creating any vapor particles at all. So even if there's a collision with the floor, I won't create vapor particles. So that's my three conditions. If all three conditions are one, or if all conditions are fulfilled, I create a vapor particle. This is a very efficient method to control the amount of vapor particles for our fluid emitter. But I'll explain more in detail later. So the next thing I want you to take note is the order of nodes in our hierarchy of the tree. So the first one is the position born. So the particle, the vapor particle, is created, and then later below is the group change. So first position born, we create the vapor particle, and then I'll move the acid particle that was used to create a vapor particle into the inactive particle group. So then this is no longer considered as a particle that can create acid. So as long as it's in the inactive group, it will not create acid again. So all the acid in this particle is used up. That's the basic idea. So very simple but efficient method to remove more and more particles from acid and preventing creating more and more vapor particles. Then what I do is when this particle enters the inactive group, I'll just change my mind. So when it enters the group, I'll start an egg timer for 10 frames, and after 10 frames I change my mind and move it back to the acid. So after 10 frames I just assume, okay, the acid has recharged and it can erode away more metal. So I'll move them first out. After 10 frames I move them back into the active acid group so they can burn away metal again. So that's a very simple but effective way to control or simulate the behavior of our acid flowing down the metal plate. And now let's have a look. If I actually wanted to have the erosion or the burning away of metal effect, I would need to work with OpenVDB volumes to eat away the part of the metal. So the first thing I'll do is I'll turn all the acid particles into a volume as well. So I want all these particles to behave as one volume, so I can actually interact with my metal plate. So we need to have two volumes in the end, the particle as a volume and the metal plate as a volume. Then we can do some really amazing, extremely fast operations on our volumes. So as you can see, I just picked the acid group with our particle to volume to turn all the acid into a volume. Then I'll grab the metal plate volume, which we have created in our create dynamic set at the very beginning with our shape to volume. So that created our metal plate volume object. So right now, let me just reset the simulation and we see it's now active. So we have the metal plate as a volume object, and I'll grab the volume particle object as well. I get the grid from the particle to volume, and I use that as an alpha mask for our filter node, the erode filter. So now the erode takes away material in those areas that are masked. So only where our particles are touching or intersecting the volume, we will erode away. The erode function will take away volume or voxels from the surface. And now, the longer we have contact with our metal, the more the acid will eat away from the metal plate. So this is a very simple, fast, but highly efficient setup to erode or eat away chunks of material from an object. And then we use the set grid to set the new result, and we eat away more and more of our volume object until it eats through the metal and burns a hole through the whole metal object. And then we go back from the volume to shape so that we get our new volume, and the cycle starts over again. We start with the eroded volume, we erode more away, and so on. So it's a cycle of that our volume object is eaten away by our acid. So it's also a very simple, straightforward setup we have here. And the only thing left is actually giving the fluid or acid a surface. And I'll just use a standard OpenVDB shape, pick the acid group with including sub-objects, and then we get our surface. And then actually we can render our surface. If we wanted to, we can render and create the animation for our surface. If we would not turn on the surface, we wouldn't see it, and now we see the surface. So very efficient method to render our surface or acid in this setup. So the next thing left is our fluid simulation, but that is finalFluid. It works in real time. So once we've cached everything, we can actually fine-tune and adjust in real time. So that's our real-time view in finalFluid. We pick the particle emitters, and now we can adjust all kinds of settings what we want. The density, more smoke, less smoke, how fast it rises up, interaction, if we want to make more smoke, and all these settings like the buoyancy, for example. I'm playing around with that, how fast it rises up, and all these things we can adjust in real time. So that's just the standard finalFluid. That's the beauty of it. And thinkingParticles is the perfect particle system to create really advanced visual effects together with finalFluid. So I hope you enjoyed this video. It's a little bit different. It's not a video from scratch, but I still think it's worth just exploring how we do setups, and you will find this sample scene in our next release of thinkingParticles as well, and then you can just grab it and check it out on your own. Thanks again for watching this video. I hope to see you again. Thank you. Goodbye.